Hey, welcome back. In this video, we're going to continue discussing complexity classes and some graph problems in those classes. In the last video, we started this discussion and we focused on the complexity class P, and we saw a bunch of examples of graph problems that are in the class P. In this video, specifically, our focus will be on the complexity class NP. And we've seen NP before. This is the class of problems where the problem instances for which the answer is yes have an answer that's verifiable in polynomial time in the size of the instance. So when we're talking about graph problems, often our instances will be graphs. So the size of the instance for graphs, for example, that would be the order of the graph. And when we say polynomial time right here, I just want to mention, like I mentioned in the last video, that we mean polynomial time on a deterministic Turing machine. In other words, a classical computer. And we have some problems which every problem in NP can be reduced to. We call these problems NP hard. So we say a problem F is NP hard if every problem in NP can be reduced to F in polynomial time. Now, that wording probably sounds vague. So here is a clearer way to see it. If we use the problem F as an oracle, so if we can ask yes or no answers of F and get them answered, then any problem in NP can be solved in polynomial time using the oracle F. One other thing I want to mention here, this is kind of implicit in the top bullet, but I like to make it more explicit. The problems in NP, these are yes-no problems. So it was slightly implicit because this part, the answer is yes. But just to make that clear, so we're talking about problems where they either have a yes answer or they have a no answer. And we've already seen a bunch of examples of problems that are both in NP and NP hard. And the term for that is NP complete. So we say a problem is NP complete if it's both in NP and it's NP hard. So these problems that we've seen before that are in NP and they're NP hard, all of them we can call NP complete. And one example that we saw in last week's videos, we saw the problem of the crossing number. So given some graph G, the problem of determining whether or not the crossing number of G is less than or equal to K for some given integer K. This is an NP complete problem. It's in NP and it's NP hard. Another problem we saw last week, which was related to the crossing number. So both the crossing number and this problem can be applied to VLSI circuit design. So the other problem is the thickness. So given some graph G, given some integer K, is the thickness of G at most K. That's also an NP complete problem. So it's in NP and it's NP hard. And we've even seen some problems before that were also NP complete, although we did not necessarily mention when we saw them that they were NP complete. But whenever we've seen NP complete problems before, we've never talked about how to prove fully that they're NP complete. So we proved for a few of them that they were in NP, because usually proving that is not so bad for graph problems. But we didn't prove that any of them were NP hard. So that's the purpose of this video, is to see how to prove that problems are NP hard and to get some more practice with proving that problems are in NP. So to prove that problems are NP hard, we're going to use this problem called Threesat. Threesat is pretty much the most famous NP complete problem. So there's a lot of research papers where they prove some problem is NP complete, and the NP hardness part of that proof they use Threesat for. And we're going to use Threesat for some results today. Like I said, it's NP complete. Before we use it to prove some other results, we should define it and see some examples. So Threesat is going to have instances which are formulas. And the formulas will be conjunctions of disjunctions. And each disjunction will have literals. So it will be a disjunction of literals. And literals are either variables or their negations. So variables, we can think of our formula as having some variables: x1, x2, x3, up to xn. And all of them are true or false. So these are not numerical variables. These are true false variables. And these formulas in Threesat, these Threesat formulas, they will be conjunctions of disjunctions of literals. And each literal is a variable or its negation. So an xi or a not xi. So if xi is true, not xi is false. If xi is false, not xi is true. And Threesat is a little more restricted than what I said. So it is a conjunction of disjunctions of literals, but the three part, that restricts it so that there are at most 3 literals per disjunction. So let's see a few examples of some Threesat formulas. So here's an F1. And here's another. Okay. So this will be a typical instance of Threesat. So here are some examples of instances. Notice that both of these instances, we write our ands like this. That's an and. This is an or. So an and is a conjunction. An or is a disjunction. And note that each of these disjunctions, so disjunctions, we write them as a string of ors in parentheses. So in these formulas F1 and F2, we have 2 disjunctions in the first one, and the second one has 3 disjunctions. And each of the disjunctions in both of these formulas have at most 3 literals. So the first formula, its disjunctions have 3 literals and 2 literals. And the second formula, its disjunctions have 2 literals, 1 literal, and 1 literal. And all of these are fine for Threesat because we just require at most 3 literals per disjunction. And the problem for Threesat is, can we assign true or false values to the variables to make F true? So let's look at that for F1 and F2. So for F1, I claim we can assign these values. So we can assign, let's say, true, 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 and true we could do. So the first disjunction of F1, x1 or x2 or x3, that's true or true or true. So that whole thing becomes true. The second disjunction right here, we have true or not true. So true or false. True or false, that's still true. So we get true for that second disjunction. So the conjunction right here, the conjunction is going to be a conjunction of true and true. So we get true. So this satisfies F1. It makes F1 true. And F2 is unsatisfiable. So you cannot make F2 true by assigning true and false values to the variables. So for these instances of Threesat, the F1 instance, the answer is yes. The F2 instance, the answer is no. Let's talk a little more about why F2, the answer is no. Why is it unsatisfiable? It's because we have these two disjunctions at the end. So we have a disjunction that just has an X4 in it, and we have a disjunction that just has a not X4 in it. And F2 is a conjunction of these disjunctions. So every disjunction must be true. A disjunction with only one literal, it means that that single literal has to be true. So we need X4 to be true. We need not X4 also to be true. And that gives us a contradiction. You can't have them both be true. So it's impossible to find any assignment of true values, true false values to make F2 true. So the answer for F1, the Threesat answer, is yes. It is satisfiable. The answer for F2 is no. It's not satisfiable. There's no assignment of true false values to the variables to make F2 true. And we did the example there. And I claim that this problem is an NP. And let's talk about that. Why is it an NP? So let's say that N is the number of variables in F. What we need to do is for any yes instance of this problem, Threesat, we need to provide a certificate of the answer yes, so proof that the answer is yes, that can be verified in polynomial time in the size of the instance. So some good evidence that the answer is yes would be an assignment of true and false to the variables of f. And we can represent this assignment as a string of trues and falses of length n, because there's n variables, and we can take those n variables, we can write them x1, x2, up to xn, and then we can just take the true-false assignment that makes the given Threesat formula true, because we're talking about a yes instance. So an instance where the formula is satisfiable. So we'll take whatever the true-false assignment is, and that is our certificate that we give to the verifier. And that's just a string of trues and falses of length n. And the verifier takes that certificate, and I'll give another example of one of these certificates. So for the instance that we saw up here, F1, that's another yes instance. Its certificate would be right here. Notice that F1 has multiple certificates we can give, and that's fine. It's possible that there are tons of certificates. All you need is a single certificate that can show that the answer is yes. So we're given the certificate, and we need to verify that it's valid in polynomial time and the size of the instance. So how to do this? Well, what we can do is we can take those true false values for the variables. So we're given variable true false values, and we can use those in polynomial time to find the true false values for all the literals. And then given that in polynomial time, we can use that to find the true false values for all the disjunctions. And then we take all the disjunctions, and if they're all true, then the conjunction is true. And if any of them is false, then the conjunction is false. So in polynomial time, that gives us the true false value for the conjunction. And so we're given this string of trues and falses, this string right here, which represents a true false assignment to the variables of the formula, which makes the formula true. And we can use that string to determine whether the whole formula is actually true for that given assignment. So given that assignment, that tells us which variables should be true and false for this valid assignment that satisfies a formula. And then we can use those true-false variables again to find the true-false values of the literals, the disjunction, and then finally the conjunction. And the conjunction is just our formula. And if we find that the conjunction is true, then it means that we were given a valid certificate. So if this is true, then our certificate's valid. So this is why the problem Threesat is in NP. It's because for any instance of Threesat, we can provide some certificate if the instance has the answer yes, and that certificate can be verified in polynomial time to prove that the answer is yes. And we're going to use Threesat in this video to prove that some other problems are NP hard. So Threesat, it is one of the most famous NP hard problems. And we're not going to prove in this video that Threesat is NP hard. So that would be its own video. But we will use the fact that Threesat is NP hard to see why a bunch of graph problems are NP hard. So we'll see how you can use Threesat to prove that graph problems are NP hard. And there are many papers where they just take Threesat and they reduce it to some graph problem. And even recent papers, this kind of proof happens often in current research. So we'll see some examples of how to do this kind of proof, even though we're not going to prove that Threesat is NP hard. And knowing how to prove that Threesat is NP hard, this is something good to know. But for proving that graph problems are NP hard, all we need to know is that Threesat is NP hard. So we don't really need the proof for our purposes today. And we talked about proving that problems are NP hard before. We said that to prove that something is NP hard, you have to provide some reduction from every problem in NP to the given problem. Now, there's an easier way to do it. So instead of finding a reduction from every problem in NP to your problem, you can just find a reduction from an NP complete problem to your problem. And so this is why Threesat is real useful. It's because Threesat, it's NP complete. So we can just use Threesat and we can do reductions from Threesat to whichever problems that we're trying to prove are NP hard. And that's what we're going to do on the next slide. So we'll start with the graph problem that we've seen before, the problem of finding an independent set. And we'll see that this problem is NP complete because it's in NP and it's NP hard. And in order to prove that it's NP hard, we're going to use a reduction from Threesat. So the independent set problem that we're going to look at specifically is given some graph G, which has vertex set V and edge set E, and some integer K. Is there an independent set of vertices in G of size K? So I'm going to leave as a problem to you to think about, why is the independent set problem in NP? So for yes instances of the independent set problem, why is there a certificate that we can use to verify that the answer is yes in polynomial time in the size of the instance? And so independent set, we said it's in NP, but now let's see why it's NP complete. So to show that it's NP complete, we need to show the other side of it, that it's NP hard. So showing things are in NP, this is like proving an upper bound on them. Showing that they're NP hard, this is like proving a lower bound on them. So showing that something is NP complete, this is a sharp result. So we're getting a sharp result here that the independent set problem is NP complete. So given this graph G and a positive integer k, is there an independent set of vertices of size k? That's our independent set problem. And it's a yes or no problem. And in order to show that it's NP hard, we're going to do a polynomial time reduction from Threesat. So we're going to show that if we have some oracle which can answer the independent set problem for us, then we can find a polynomial time algorithm to solve Threesat with that oracle. How are we going to do that? Well, we're just going to take an instance of Threesat and we're going to turn it into a graph. So there's an instance of Threesat, some Threesat formula F, which is a conjunction of, we'll say, k disjunctions Fi of at most 3 literals. So let's take the example we saw before. So x1 or x2 or x3, and we'll do x3 or not x4, let's say. And let's actually add one more variable to that one. So we'll do a slightly different one than before, just to make this one illustrate the reduction a little better. So let's make it not x2 or x3 or not x4. Okay. So we have x1 or x2 or x3 and not x2 or x3 or not x4. So the number of disjunctions, we have k equals 2, conjunction of k disjunctions. And here's our F1, here's our F2. And each of them has at most 3 literals. So what we're going to do here is we're going to construct a graph G. And this graph G, each of the disjunctions, we will build a clique representing that disjunction. So for each disjunction of size 3, we will make a triangle of vertices vi1, vi2, vi3. And we'll have edges between each of the vertices in the triangle. I'll mention this triangle, it can be degenerate. So some of these vertices we may have repeats. So as you see, some of the disjunctions in these Threesat formulas that we saw in the previous slides, some of them have fewer than 3 literals in them. So they only have to have at most 3 literals. So if they have fewer than 3 literals, this is fine. We will, instead of having 3 distinct vertices here, we could have 2 or 1 vertices there. And between all the vertices, we will put edges. So each of the vertices in this triangle, whether or not it's degenerate, each of the pairs of vertices will have edges between them. And we're going to also add some extra edges. So let's take the example we have at the top, the F formula, and we'll draw our triangles. So we're going to have the F1 disjunction here. We'll get a triangle from that, which will have V11, V12, and V13. And we'll also have another triangle, which is V21, V22, and V23. And this V11, so the V11 represents the X1, the V12 represents the X2, and the V13 represents the X3. The v21 represents the not x2, the v22 represents the x3, and the v23 represents the not x4. So we want to put an edge between any vertices in different triangles, so any u and v in different triangles that represent a variable and its negation. So we look up here. When do we have some vertices down here that represent variables and their negations up here? Well, in that first triangle, we have the x2, so this v12 right here. And the second triangle, we have the not x2. So in this disjunction f2, we have a not x2 there, which corresponds to the v21 right here. And so we want an edge between those two as well. And I'm going to erase some stuff now so we can see it better. Okay. So that's what our graph looks like, corresponding to the formula F. And there's only those two vertices that are in different triangles which have an edge between them, because those are the only two that represent a variable and its negation. And I'll mention again, if any of the disjunctions had fewer than 3 literals, instead of using a triangle, we would just use a K2 or a K1. So I claim that G, the graph that we started with, G, the graph that we just constructed, the graph we constructed, G, has an independent set of size K if and only if the formula F that we started with can be satisfied. And we're going to talk about why that's true, but I'm going to move this picture so that we have some space to work with. So I think I'll just put it up here for now. So in order to prove this if and only if, we have two directions to prove. So we'll start with the direction where we assume that G has an independent set of size K, and we'll use that to prove that F can be satisfied. So if G has some independent set, we'll call it I, of size K, then we can look in our graph that we constructed, and we can see that there are a total of K triangles, because we had this formula F, which was a conjunction of K disjunctions. Each disjunction, we made a triangle for it, and in each triangle, we cannot have more than a single vertex from the triangle in the independent set. So if two vertices from the same triangle were in the independent set, that would give us a contradiction, because independent sets cannot have vertices with edges between them. So since our independent set has size K, we know that every single triangle has to have a vertex in the independent set, because there can't be any triangle which has multiple vertices in the independent set, and there's only K triangles. So every triangle has some vertex in the independent set. And remember that these vertices in the triangles correspond to literals in the disjunctions. Also, note that for this independent set in our graph that we constructed, so independent set in this graph, we can't have any vertices in the independent set which represent a variable and its negation, because between any pair of vertices in different triangles which represented variables and their negations, between them we put an edge, and this is an independent set I. So we can't have an edge between any two of them, so there can't be any two of them that are a variable and its negation in I. So that means that if we take any true-false assignment which makes all the literals true that correspond to the vertices in I, because remember, all the vertices in the graph that we constructed correspond to some literals. So if we just take all the literals in our independent set I, and we take any true-false assignment which makes all of them true, then that must satisfy F, because in our independent set, we have a single vertex from each triangle, which means that we have at least a single literal from each disjunction is true in F. Because, again, each of the vertices in the triangles correspond to literals in the disjunctions. So this is why if G has an independent set of size k, that implies that F can be satisfied. So again, this true-false assignment, there might be multiple choices for the true-false assignment. All we require is that it's some true-false assignment which makes true all the literals that correspond to vertices in I. So we might have multiple choices for some of the true-false values in this true-false assignment, but as long as all of the vertices in I, as long as the literals corresponding to them are made true, then this will satisfy F. So now let's look at the other side of it. So why can we say that if F can be satisfied, then G has an independent set of size k? So again, we construct our graph G, we make the triangles, we put edges between the vertices and the triangles. The triangles, again, they may be degenerate. So we might have triangles which are actually K2s or K1s. This is fine. And we also add edges between vertices in different triangles that correspond to variables and their negations. And here's what we're trying to prove, this if and only if. We already proved the forward direction of it, that if G has an independent set of size k, then F can be satisfied. So let's now prove the backward direction. So if F can be satisfied, then G has an independent set of size k. So if F can be satisfied, then we know that means there is a true-false assignment to its variables, x1, x2, and so on, such that each of the disjunctions in F has at least one true literal. So we can take the graph G that we constructed, and we can color the vertices in G that correspond to the true literals in F for this true-false assignment, which makes F true. So if F can be satisfied, we have this true-false assignment X, and we use this true-false assignment to color any of the true literals in F. And the things we're coloring, we're not coloring the literals, we're coloring the vertices which correspond to the literals. So since F is satisfied by the true-false assignment X, and since we're coloring the vertices in G using the true-false assignment to determine which literals in F are true, and again, we mentioned before on the previous slide, each of the triangle corresponds to a disjunction. And again, we know each disjunction has at least one literal that is true for this true-false assignment because the true-false assignment makes F true. So each triangle has to have at least one colored vertex because we're coloring vertices that correspond to true literals in F, and F is true. So each of the triangles must have at least one colored vertex because each disjunction must have at least one true literal. And this might not be an independent set, this coloring we have. So if we take the colored vertices, if we have any triangle with more than one colored vertex, that would not be an independent set because we can't have two vertices from the same triangle in an independent set. So we just uncolor all but one vertex from each triangle. And we still have every triangle has at least one colored vertex now. It's just every triangle also has at most one colored vertex now. And there's k triangles. So we have an independent set in the graph of size exactly k. There's a little more to say about why it's independent. So we don't have any edges between vertices in this independent set because if we had some vertices in different triangles and they correspond to a true-false assignment that are for a variable and its negation. So if we had two vertices in different triangles, these vertices cannot be in our independent set if they correspond to a variable and its negation. So you cannot, because we put an edge between these vertices in the graph G. So this step right here, if U and V in different triangles represent a variable's negation, we have an edge between those variables. So in our independent set, we can't have edges between any of the vertices in the independent set. So we won't have any edges between vertices in this set that we made. And I just want to clarify the I here. So we have an independent set I and G. So this I is just the colored vertices. So we colored vertices, we uncolored some of them. The vertices that we end up with that are colored, that's our independent set. And there's not going to be any edges between vertices in this independent set because all of the vertices are from different triangles. And two vertices from different triangles that represent a variable and its negation cannot both be in the independent set by how we constructed G. So this is why we get the if and only if here. So G has an independent set of size K if and only if F can be satisfied. And now we can see that we actually have a polynomial time algorithm to solve Threesat as long as we can use independent set as an oracle. So we take any Threesat formula F. We convert F to a graph G. We determine if G has an independent set with size equal to the number of disjunctions in F. If so, then F can be satisfied. And if not, then F cannot be satisfied. And that's it. So that way we can just ask the independent set problem as an oracle if there is an independent set whose size is equal to the number of disjunctions in F, and we get a yes or no answer. So that tells us whether or not F can be satisfied. So that finishes the proof that the independent set problem is NP hard. And we're going to see some other problems, and we're going to see with them that it's much easier to show that they are NP hard. So the first one we'll look at is Clique. So if you're given a graph G with vertex at V and edge at E and a positive integer K, can you find a clique of size K in the graph? And I'll leave as a problem to you to tell me, why is the clique problem in NP? So why, for yes instances of the clique problem, so for graphs G which have a clique of size K, why can we provide a certificate of this fact that can be verified in polynomial time in the size of the instance? And we'll look at in this video why the clique problem is NP hard. And this proof will be much simpler than the proof that independent set is NP hard. And instead of reducing from Threesat, we will reduce from independent set. That's why it's going to be easier. And we know independent set is NP complete, so it's fine to use independent set as the problem that we reduce from to show that clique is NP hard. So in order to do this reduction, we'll take some instance GK of the independent set problem. And we need to show that if we have some oracle which can answer the yes or no questions for the clique problem, then we can use this to answer the independent set problem in polynomial time in the size of this instance GK. So we'll let G prime be the complement graph of G. And I claim that G prime has a clique of, so I claim here that G prime right there, has a clique of size K if and only if G has an independent set of size K. And how can we see that? Well, if G prime has a clique of size K, we can take those vertices in that clique, V1 up to Vk, we'll call them, in G prime. And if they make a clique in G prime, it means that there's edges between all those vertices in G prime. Since G prime is the complement graph of G, it means that in G, there's no edges between any of those vertices. So those vertices form an independent set of size K in G. And in the other direction, if G has an independent set of size K, we can argue it similarly, that whatever those vertices are, v1, v2 up to vk, with no edges between any pair of them, in the graph G prime, they must have edges between all of them, so they must form a clique of size k. So G prime has a clique of size k if and only if G has an independent set of size k. So our algorithm is we take our instance gk right here, we calculate the complement graph of G, call it G prime, and then we ask the oracle, does the complement graph have a clique of size k? If it does, then we can say G has an independent set of size k. And if it doesn't, we can say that G does not have an independent set of size k. And so this gives us a polynomial time reduction from the independent set problem to the clique problem, because we're using the clique problem as an oracle to solve the independent set problem. And I'll leave this part as a problem to you though. Why does constructing the complement graph G prime take polynomial time in the size of G? And here's another one that we can prove is NP complete. So we saw that independent set is NP complete, clique is NP complete, and now vertex cover here. So vertex cover, given a graph G and a positive integer k, is there a set of vertices of size k that are adjacent to every edge in G? So for example, let's say G equals this graph, and k equals 1. And let's consider another one. Over here, we'll say G equals this graph. And k equals 1 there. So is there a set of vertices of size 1 that are adjacent to every edge in G? Here, there are. So found a vertex of size 1 there. It's adjacent to every edge. Every edge touches that vertex. Every edge contains that vertex. In this one, is there a set of vertices of size k that are adjacent to every edge in G? And the answer is no for this one. So there's no vertex there, no single vertex that's adjacent to every edge in G. So this vertex is adjacent to almost all of them, but it's not adjacent to that one. So that's what messes it up. So the answer would be yes for this instance, but no for that instance. And that's an example of it. And here's a problem. Why is the vertex cover problem in NP? So that's a problem for you to think about. And remember that showing that a problem is in NP, all you have to do is show that for yes instances of the problem, there exists some certificate that you can use to verify the fact that the answer is yes in polynomial time and the size of the instance. In this case, our instances are these graphs G and the positive integer k, which we can assume is at most the order of G. So the size of the instance we can just take as n, the order of G. So I'll leave that problem to you to think about. Why is the vertex cover problem in NP? So why can you provide a certificate for the yes instances that you can verify in polynomial time? But we'll do this part together, showing that the vertex cover problem is NP hard. And to prove that it's NP hard, we will do another reduction from independent set. So we know independent set's an NP complete problem. So we can just do a reduction from any NP complete problem to vertex cover to show that vertex cover is NP hard. And to do this reduction, it's going to be even simpler than the reduction that we did for the clique problem. And this reduction, we don't even need to change the graph. We use the same graph. And all we have to do is, in order to answer whether some instance gk, so an instance gk for independent set, In order to answer whether or not the instance has a yes or no answer, we just take the graph G, we don't do anything to G, we just keep it as it is, and we see if G has a vertex cover of size n minus k. And I claim that G is an independent set of size k if and only if G has a vertex cover of size n minus k. And I leave that as a problem for you to think about. So this problem is for you to think about, but given that problem, the if and only if right here, then if we want to answer whether or not this instance is true or not, so does G have an independent set of size k, we can just ask the oracle for vertex cover, does G have a vertex cover of size n minus k? If the answer is yes, then the answer for this one is yes. If the answer is no, then the answer for that one is no. And that gives us a polynomial time reduction from independent set to vertex cover. And the reduction is real simple. We didn't even have to change our graph G. We just ask the vertex cover oracle about a different integer than k. So instead of k, we use n minus k. Although if k equals n over 2, then of course they're the same. So that brings us to the end of this video. Thanks for watching.